it works out. And I'll go faster at the end of lecture in particular. So I'm going to talk today about a really cool data structure, okay, which is called Emde Boas. Emde Boas is also a person, a researcher in computer science. He usually does model theory, I guess. But at one point, he took a stab into data structures. And he's one of the few computer scientists to also be a verb. But I'll say why later. So this data structure is usually called Emde Boas or Emde Boas priority queues or successor trees, whatever. It solves something called the fixed universe successor problem. Okay, which has a fancy name, but it's something you're quite familiar with. You want to maintain a dynamic set, okay, like most data structures. Except now you know something about the set. It's not just an arbitrary set of numbers. You know what the universe is. So you want to maintain some set of size n of some universe U and the universe is known to be the numbers from 0 up to u minus 1. So it has size u, which is conveniently an upside-down n. Okay, so there's some kind of parallelism here. And you want to maintain this set subject to the usual sort of operations, but I want to be explicit about what those operations are. You want to be able to insert any element. So if we have some element x that's in our universe but not yet in our set, then we should be able to insert that number x. On the other hand, if we have some x that's in our set, we should be able to delete it. And then the key thing is successor. That's why it's called the successor problem. Is I can give you any element in the universe, and I can ask for the next element that's in S. So the key here is that X is any element in the universe. Okay, I'll rub that in. For any element in the universe, I can find the next greater element in my set S. That's the successor problem. And you presumably also want predecessor. Put that over here. Okay, so we have some data structures for this problem. Who can give me some data structure we've already seen that solves this problem in some amount of time? Easy warm-up question. Linked lists. That works. Another suggestion? Binary search tree. Good. Yeah, so linked list. Let's do them. So here are some solutions. You just have a linked list. What's the running time of these operations?
Depends if it's sorted or not. It's not sorted, inserts just order 1, deletes order n, and successors order n.
So if it's not sorted, if it is sorted, then insert is order 1, delete is order n, you said?
Yeah.
And successor is?
Order n if it's unsorted.
Is order n if it's unsorted. Right. The tricky part is even if the linked list is sorted, finding the successor from any element in the universe, if you don't know where in the list you should start looking, it's kind of hard to find the successor. So I think even for sorted lists, it's going to take linear time, order n time per successor in particular. And insertions and deletions, it depends exactly. If you're given a pointer to the element in the list, then yeah, that'll just take constant time and so on. Okay, but let's go on to more exciting things. Binary search trees. So let's say balanced search trees. So what's the running time of these operations for balanced search trees? Sorry? Log n, and then, right. Someone want to fill in the We actually mentioned this in a corollary at one point, a long time ago, so it's OK if you don't remember it. But if you think in a binary search tree, balanced binary search tree, I give you some node. I want to find the next larger node in the in-order traversal of the tree. OK, so maybe let's do a little example. Here's a very simple binary search tree. If I want to find the next node after this guy, it's this one in the in-order traversal. And essentially, you just walk up like this. It takes logarithmic time. Okay, you should think about that. So in order log n time, you can do all of those operations in a balanced search tree. OK. We want to do better. Okay, and this is somehow, this I would say is the most surprising result in data structures to me. Okay, this I thought was just so cool. So I'll give you some context. In 1975, Peter van Emde Boas solved this fixed universe successor problem. In order log time. A little catch is that it's log u and not log n. Okay, but so u again is the size of the universe. And so in particular, if u is not too much bigger than n, if it's only polynomial in n, then this is order log n. Okay, that's fast. That's exponentially faster than balanced search trees. Okay, now these two data structures, they didn't use the fact that the numbers were taken from this universe 0 to u minus 1. Okay, and without that assumption, balanced search trees are optimal in some sense. But once you add in this u parameter, that all the numbers are bounded by at most u, you get log u time, which is really fast. Okay, for as long as u is less than the number of particles in the universe, log u is at most 8. Okay, for all practical values that you will probably see in your lifetime, log u is about 6. I think this is true. Okay, it went up recently from 5 to 6, but it's not going to go up again, I expect. Okay, so that's fast. This is cool. Okay, so the first thing you might ask is, well, how the heck are we going to get log u? We've seen log, we've seen n log n. Where might we get, this is a problem for you to think about, where might we get log u? I mean, forget the fact that it's u and not n. Where do you get a log bound? Any ideas? We've seen log all over the place. Last time we saw log squared because you were doing logarithmically many things. For each one, you did another logarithmic thing. So you multiplied them together. But here we're getting log of log. Do you have an idea?
We were to find log u like balance search tree or something like
Right.
the interval trees, if we were to use log n node instead of n node, then we would have log n to find something.
Okay, so if somehow we had log u nodes already from like a balanced search tree, and then within of those nodes we had another balanced search tree, is the height of that tree is log n. Yeah, that's one way you could do it. So you could have a search tree. So you could have a search tree over order log u nodes. Okay, if we had log u nodes, then the height of this search tree would be log u. Another related thing is you might do a binary search over log u nodes. Sorry, over log u nodes. Okay, that'll also take log u time. Or numbers, elements, whatever. Can anyone tell me a recurrence? What's the simplest recurrence whose solution is log u? Sorry. So T of u is, I have to think. Log u. What should we do? Okay, I'll give you a hint. That's not much of a hint. But let's say that the last term is just a constant. What should we do to u to make this come out to log u? It should go in here. If we said u over 2, that would give us log n. Because the number of times you have to divide u in half till you get down to a constant is order log n. So yeah?
Log u over 2.
Log u over 2. That would go a little too fast, I think. So you're suggesting log u over 2. So this is how many times do I have to take log and divide by 2. So let's ignore the divided by 2. How many times do I have to take log before I get down to a constant? That's something else. That's called log star. How many people have seen log star? About half. Okay, this would give log star. It means how many times do I have to apply log before I get down to 1? Or at most 2 or something. Okay, so I claim that's not quite right. That's actually smaller than log n. Some more ideas? Yeah? Square root of u, right. How many times do I have to take square root before I get down to a constant? That's exactly log u. Okay, in some sense, this is the only way you can get log u. I mean, it's the most fundamental thing you could have, some kind of recursive algorithm or something that takes something of size u, reduces it to size square root of u. That's the fundamental place you get log u. Okay, it's hard to think of another way other than this kind of thing. Why don't I rewrite this so it's obvious this is log u. So this gives log u now. If I reparameterize by log u, okay, then I'm getting, if I take square root, that's the same as dividing the logarithm in half. Okay, so this is close to what you were saying before, right? You said log u over 2. That's right, as long as you start with just log u. Okay, each time you divide the logarithm in half, well, if I replace log u with x, then this is x going to x over 2, so that's log x. X is log u, so that's log u. Okay, so I mean, you can apply the master theorem at this point and say, well, that's log u. Okay? So that's where we're headed. We need to somehow take a problem of size u and reduce it to a problem of size root u. And what I would like to do with this lecture, it's good there's large attendance today because there's a problem set. This is a good lecture to attend. Because what I would like you to do is for you to give me a data structure that runs in log U time. So you're going to do what Van Emde Boas did. This should be fun. Okay? I'll lead you in the right direction, but the ball is in your court. You have to do the work. Okay? It's not because I'm lazy. It's because you'll learn. OK, we need a starting point. We're going to start with some very simple data structure, so the simplest thing you could think of. And we're going to bootstrap our way up from there. So what's like the simplest thing we could possibly do? I mean, even simpler than linked lists in some sense. So I want to solve this fixed universe successor problem. Yeah?
Array.
An array. Good. So this will be our starting point. It's an array. Now, what should we put in the array? Any proposals?
Data.
Data. Good answer. What kind of data? Yeah.
The numbers from S.
The numbers from S. Yeah, that's one thing we could do. That's not actually what I'll use. But one thing you can do is an array storing the numbers in S. OK, so it's actually not going to be the simplest thing you could think of. So this is not our starting point. So let's, for example, let's suppose we have the set 1, 9, 10, and 15. And the size of our universe is 16. Then what you're proposing is an array. Looks like 1, 9, 10, 15. But let's analyze this. Let's see how this goes. And then we'll think of something else. OK, so how long does it take to do a successor query in this array? OK, I presume you meant sorted order. Seems like a good thing. Log n time, yeah. Or, yeah, log n, right. So here are successors in log n. Just do a binary search. And insertion. Anyone else? Inserting into a sorted array. As we've said it, we want to keep them consecutive. So that's going to take order n time, right? OK, it's not good, but that's fine. I mean, our starting point will not be good. OK, I'd like to start with a different bad data structure than this one. Can anyone think of another way to use an array to solve the fixed universe successor problem? Yeah.
Maybe an array the size of U, where you have a 1.
Right.
Is the right.
Right. You have an array size of U, and you have a 1 every time you have an element in S. Right. That was mentioned in lecture some time ago when we were talking about hashing. That's called a bit vector. I think we mentioned that, didn't we? Yeah. OK, so our actual starting point will be a bit vector. OK, I mean, this is a reasonable starting point, and it actually gives you a different data structure. OK, but I want to use a bit vector for the purposes of Van Emde Boas. OK, so it's a vector indexed by some element of U. So say x in U. And then v sub x, v is my vector, stores 1 if x is in the set, and 0 if x is not in the set. OK, so that's sort of the next simplest thing you could imagine. So in this picture, this example, I have some array of size 16 now. So each of these is indexed by some element in the universe from 0 to 15. And the elements that are present in this set is the number 1, the number 9, the number 10, and the number 15. And everything else is marked with a 0. OK, so that's the bit vector. That's our starting point. What are the running times of my operations? OK, how quickly can I do an insertion in this data structure? Order 1, right. You just set a bit. Deletion, same thing. OK, I'll just concentrate on insert and successor for now. Actually, probably for most of the lecture. OK, insertion takes constant time. I just set a bit, turn it from 0 to 1. What about successor? Could take order n. That's true. Any other answers? Order u, right. It's actually worse than order n. And it could be I just have one bit set way over here. I find the successor of 0, I have to walk all the way down this string. In general, if I have some position I want to find the successor of, like 4, I just look there, look at the next position, until I find a 1. That's my successor. Okay, in the worst case, I have to go all the way through the array. The array is of size n, of size u. Add this bit vector of length u. Okay, this is also bad. Okay, like the one we had before, where insertion was expensive. But we're going to make it better. Okay, I want you to think about how we could make it better. And we need to think about this target. Okay, let's suppose, let's not worry about the full recurrence. But let's say I just want to take a problem of size u, which is what I have there. I want to reduce it to a problem of size root u. How could I do that? How could I take this bit vector, break it up into smaller bit vectors? Any other ideas? Go ahead. Everything in a square. Yeah. That's essentially what I want. Where should I go here? So if we arrange those bits into a square, then the dimensions of that square will be root n by root n. OK, so let's do it that way. So this is the second idea. The second algorithm, data structure. Arrange the bits into a square. I think that's a good way to think about it. So here, in this example, u is 16. So root u is 4. So I could take the first 4 bits here, then the next 4 bits, and the next 4 bits. I just drew that in the wrong spot. Copy the numbers over, 0, 1, 0, 0, all zeros, and 0, 1, 1, 0, and 0, 0, 0, 1, I believe. OK, and the point is, in this dimension, I have root u different groups. And here, each group is the size root u. OK, that's the idea. Okay, so another way to say this is that I'm splitting my universe of size u into root u pieces, each of size u. I'll call those pieces widgets. So I'm going to get square root of u widgets. And each widget is of size root u. Okay, so this is a widget. Each of these is a widget. So a widget just consists of some consecutive cluster of bits. Okay? So is this a data structure? Can we see how to do insertions and deletions? How could we now use these widgets to do insertions and deletions? Well, insertions and deletions, they were fast. How can I do successors faster now that I've broken up my universe into pieces? I mean, so far, we haven't really done very much. But there's something that we can add on. We can augment this data structure with a little bit of information. And very quickly, or not very quickly, but faster, we can find successor. Yeah?
Have like an extra piece of information saying if there's a 1.
Right, exactly. Have an extra piece of information. Let's put it at the end here. I'll put it with a circle just so it looks different. It says, yes, there is a 1 somewhere in here. Okay, here, there's no 1. Here, there's a 1. And here, there's a 1. So this is just the OR of all the bits in the widget. Okay, so suppose each widget stores whether it's empty or whether there's someone in there. Sorry. Each widget says whether it's non-empty. Okay, now how do I do successor? Or how, maybe ask, what's the running time of successor? It's hard to communicate algorithms over voice. Either one. How about in the back there? Square root of u, right. And how does it go? You want to?
So use the check to see if the extra bit is 1, and this goes down until you find one that is.
Okay. So let's say we want to find the successor of this bit. What you're saying is, first I'll look inside the widget and see if I can find a successor within the widget. So in this case, I do. I start at the 0. I just look over to the right. I find a 1. That's my successor. On the other hand, if I try to find the successor of this bit, I walk to the right and I fall off the edge. That means there's no successor within this widget. So I have to go to another widget. And then you're saying, you just look at the widget level and say, oh, I don't have to go through this widget because it's completely empty. I can tell just by looking at one bit that there's nothing in here. So I'll go until I find a widget that's non-empty. And then I start from the left-hand side until I find a 1 bit. So this 1 bit is the successor of this 0. Okay, if you look back, this is position 2. This is position 9. So back in the original picture, it's saying the successor of 2 is 9 because I could jump over this widget all at once because it was all zeros. Okay, and the claim is that that's order root n. So let's write down this, root u. So the successor algorithm is, maybe I should use a little bit more space. How long? Yeah. Some erasers have a mind of their own. So if I want to find the successor of x, first I'll look through the widget that contains x. For a successor. Okay, I'm going to make this algorithm in more detail and say what it what it's doing in a moment. But the basic outline is first I look within my widget, one containing x. If there is a successor, we're done. So if we found one, then return it. Okay, but otherwise, we have to skip along and find the next non-empty widget. After this one. And then we have to find the smallest element within that widget. And that's our successor. Okay, this is a little vague. So I want to fill in how we do all of these steps. All right. Okay, what am I going to do here? Let's see. Let's say consider the binary representation of my number x. Okay, it has a bunch of bits. In this example, u is 16, so log u is 4. So it has 4 bits. Okay, so let's say, for example, we want to index position 9. 9 in binary is 1, 0, 0, 1. So if x equals 9, we get this binary representation. Now, in this algorithm for finding the successor, we need to find the widget that contains x. I'd like to do that just using x itself, okay, using its binary representation. So which widget is x in? Okay, I should have given the widgets names, I'm afraid. So let's give them some names. Call the widgets W0, W1, and so on. And there's square root of u of them. So the last one's called square root of u minus 1. And let's be explicit. So widget w sub I represents a contiguous sequence of bits in the original bit string, bit vector. So in general, you start at I times square root of u. Okay, because each widget is of size square root of u. So once we get to the ith widget, we start at that position, and you go up square root of u steps. So that's I plus 1 square root of u minus 1. Okay, that's a bunch of elements in the universe. So this is just a description of what we've done so far. So now I have labels, right? This is called W0. This is called W1. This is called W2. This is called W3. So which widget is x in? 2, right? So the widget is in widget W2. So does anyone see the general principle there? As an example. I like proof by example.
The high order bits are the widget, the low order bits are the index.
Right. The high order bits are the widget. The low order bits are the index within the widget. That's the claim. So I give these names. The high order half of the bits encodes some number. Here it encodes 2. I call that high of x. The low order bits also encode a number. The lower half, here it's 1. And the claim is the reason it's 1 is if I look at within this widget, this is position 0, this is position 1, 2, and 3. Position 1 is my element x. Okay, so this is pretty cool, actually. So if you want to define these things without binary notation, you can say, well, I want these functions high and low. They have to be non-negative. And they have to have the property that x is square root of u times high of x plus low of x. Okay, this is basically base square root of u. Right? There's the low order half, smaller than square root of u, and there's a high order half, which is also smaller than square root of u. When I multiply it by square root of u, it gets pushed to the left into these positions. Okay, so this implies x is an element in the universe, so it's at most u. That means that high of x and low of x are at most square root of u. Okay, so this is, not only does this provide a more formal definition than the binary representation, it also provides a connection to over here. Because you see a widget represents the numbers from I times square root of u to roughly I plus 1 times square root of u. Okay, so the high part, the higher order bits, are saying how many times do I have to multiply by square root of u to get in the right range? And then once I'm in the right range, how much should I add to get within the right position in that range? Okay, so that means high of x is giving you the index of the widget. So which widget that contains x. And low of x is giving me the index or the position within that widget. So this index is called I here. Okay, so now we start to get some pieces for filling in this algorithm. Okay, so we want to look through the widget containing x. Well, that's w sub high of x. High of x gives us this index. So now we know which widget to look in. Okay, we want to look through that widget for the successor of x. So where should we start our search? Low of x, pretty much. Low of x plus 1. Okay, we want a strict successor. So we look at the position right after where x is within this widget, and we'll look through. That'll take at most how much time? To look through one widget will take square root of u time. You have a question?
W sub high of 1, low of 1.
That would work too. So the question was whether we should start looking at high of x plus 1, right? And low of x plus 1 instead of this plus 1. You could do that as well.
First widget.
Right. Yeah. If x happens to be the last guy in its widget, this will be a rather trivial search, but it won't hurt our time bound. So you could do it that way, but it won't affect the outcome. Okay, because this is at most square root of u. And now, once we start looking for the next non-empty subwidget, well, this is the smallest I. That's how it goes, right? This is Professor Leisterson's nice terminology for such that notation. Such that W sub I is non-empty. Sorry, I should say that I is strictly greater than high of x. Okay, so this is just notation, but it's saying I want to find the next non-empty subwidget. Well, I just looked at this widget, W sub high of x. So look at all the ones whose index I is strictly greater than high of x, because I already looked through that one. I'll look until I find one that's non-empty, and then I'll search within that widget and find the smallest element. Okay, so how long does this step take, finding the next non-empty subwidget? That's a tricky one in some sense. That's where all the interesting stuff is going on. Yeah?
Isn't it also order root u?
It's also square root of u. And the reason is we stored these bits that said whether a widget was empty. And so you just look through the widgets. There's only square root of u widgets. So you could look through all of them if you wanted, until you find a 1 bit. And so it takes at most order square root of u time. And then how long does it take to find the smallest element in that widget? There might be fancier techniques, but it's at most square root of u. Okay, so this whole algorithm runs in order square root of u time. Okay, now the other thing we should do is insertions. So which one should I get rid of? So if I want to insert x, this is a lot easier. We did the hard one first. How should I insert x into this structure? Okay, we knew how to do it with a bit vector, yeah?
Yeah, just set the bit at w high of x plus 1. Or no, the w high of x, like that widget at index low of x.
Right.
Set up to 1.
Right. Take the widget w high of x. And take that widget dereferenced at position low of x and set it to 1. Okay, that's just setting the right 1 bit. Okay, the tricky part here is we have to navigate which widget we should look at. Anything else we should do? Yeah.
Shouldn't we also set the indicator to be 1?
Right. We should also set the indicator. Good. So let's say this is non-empty is the indicator. We want to say that this widget, we just put something in there. So it's definitely non-empty. If it was empty before, we need to set this bit. So each widget, like w sub high of x, has this non-empty indicator. Also set that to 1. Good. That's it. So how long does this take? Constant time. So inserts are still fast. Now we have successors running in root u time. So that's better. And in some sense, it's matching the recurrence that we wanted. We take a problem size u. We split it up into, in this case, root u subproblems, each of size root u. So what should we do now? That was the second step. What should our third step be? Yeah. Make each widget into a square, yeah. Recurse. Okay, that's the third idea. There will be 5 ideas, okay? So we're about halfway. Third idea is recurse, right? We have this reduction goes from u to root u. If we could keep doing that, we get something that somehow splits into log u depth. Okay, recurse. So the particular proposal is to take each widget, do the same thing, split it into a square. Okay, that's exactly what we'll do. Let's see. Okay, so instead of, well, let's do the example first. So we take these bits, and I'm going to carve them. Take the first widget 0, 1, and 0, 0. I'll put them like that, and this is my first widget. And then the second widget, carve them into a square. Okay, here they're all zeros. The next one is 0, 1, 1, 0. And then the last one is 0, 0, 0, 1. Okay, this is giving me, first of all, a decomposition into 4 top-level widgets. And then each widget is split into 2 sub-widgets, okay, of equal size. Okay, in general, when you have something of size k, you split it into root k sub-widgets of size root k. Okay, let's write that down. So I'm going to represent my universe, U, as one big widget. So the size of the biggest widget is U. Okay, and then each widget will be subdivided. So I'll denote the size of a widget W as vertical bar W vertical bar. So that's the range of the universe that it represents. So we're going to carve each widget into square root of its size, subwidgets. So each one is of size square root of the size of W. Okay, I'll give those subwidgets names. This is sort of like C notation. Okay, so there they are. There's square root of W of them. Starts at 0, goes up to square root of W minus 1. The idea is that sub bracket W is a field associated with my widget W, and it's an array. Okay, so I can index that array by up to however many widgets there are, minus 1. And that'll give me all of the subwidgets of my widget W. Okay, so that's the recursive construction. We want some more. So maybe we should think about what's going on here. We're looking at the successor. We need to somehow recurse, right? So far, we just have an algorithm that runs in root U time. Now we want to somehow use this more general recursive construction. I mean, what's this doing? First step. Can I use recursion in the first step? You have a 50% chance of being right. Yes or no? Can I use recursion here? Someone should say, okay, if you answer yes or no, you don't have to give a justification. So this is the easy part, yeah. Yes, right, good answer. You can use recursion here. Why? Sorry? Yeah? Change I of x and how it's represented. I of x. Yeah, so this is a widget. In general, it's a subwidget, right? And what operation am I doing on that subwidget? Scanning to the right, which is successor, right? So that's a successor operation. Okay, this is successor. Okay, this is sort of the insight. Okay, I've got two more things I want to do. Let's do this one. It's easier. Returning the smallest element in the widget that you found. Can I use recursion there? So the way we were doing it in this structure is to find the smallest element. I look at the first element. If it's 0, I need to keep going. I keep going until I find a 1. Okay, that's a scan to the right. But can I somehow write that recursively? Yes. Right. Is this too easy? Who thinks it's too easy? TA. Okay, good. It's not too easy. So why can we do it recursively?
Because you can take that widget and split it up into subwidgets and look at the markup each of them.
Right, I could take that widget, split it up into subwidgets. That's what we're doing in this picture. And then what operation am I doing on this subwidget? Successor of like minus infinity. Right, exactly. So this is also a successor. Right, this is successor of minus infinity of this subwidget that we found. Okay, W sub I is what it was called. So that's a successor query too. This is looking good, right? If we could just, this is how to write successor in terms of itself. So that means successor will naturally walk down this subwidget structure. Okay, I should draw the picture here, right? If I have some widget W, we split it into a bunch of subwidgets. Sub W0. Okay, that's of size square root of W. That's the general picture. So all of my widgets are going to look like this. They're subdivided into these subwidgets, square root of W, square root of the size of W of them. Each one is of size square root of W. So what I would like is successor to call itself on a smaller subwidget. And then the recursion will go through. Okay, but I've got one more thing I need to do. Finding the next non-empty widget after a particular widget. Now this is where we use these summary bits. Right? These bits said, you don't have to look in this widget. It's completely empty. That's if it was a 0. If it's a 1, well, then there's something interesting in there, so you should go there. Okay, can I somehow use recursion for that step as well? 2 people have it. They got the other steps too. Anyone else see how to do the third step? Or the middle step here? How do we find that? Yeah. Look at the indicators for the subsets. Right. So we want to use these summary bits. So what should I do with those summary bits? How should I look at them? Sorry?
As another widget.
As another widget, exactly. So these summary bits, well, it's just another bunch of bits. I could throw them into a widget as well. Okay, so I'm going to have another widget out here, which is called summary of W. So in fact, every widget of size W will have square root of W plus 1. There's another subwidget of size square root of W. Okay, I need some space. There's never enough space. Okay, I'll go up here. Okay, so each widget W also stores a summary widget. And the notation for the summary widget is just summary square bracket W. And the summary widget is of size square root of W also, square root of the size of W. Okay, and the summary widget stores exactly, oh, they're right here, exactly these bits. Okay, these summary bits which tell you whether there's anyone in the subwidget. Okay, so this is storing which subwidgets are non-empty. So now I want to look at what are the insertion and the deletion, the insertion and the successor operations. Okay, this is where you have to help me. So I want to do the same sort of thing. Insertion should be the easy one. There isn't a lot going on. Okay, it used to be I was playing around with bit vectors. Okay, but now I'm not going to use bit vectors at all. Okay, so these steps won't really be there. The same principle should be there. Okay, I'm going to mimic exactly this algorithm, but now I want to use recursion. So what should the first line be? Okay, this is the first time we've asked you to come up with the pseudocode, okay, because it's easy pseudocode. So what this is saying is I want to look at a particular subwidget. So let's change the parameters. Okay, I want to insert X into a widget W. Okay, this, by analogy, is the subwidget with label high of X. Okay, and I want to say, well, now low of X is present in that subwidget. That's the recursive insertion. So how should I write that? If low of X is empty, then we just insert it there. Yeah, we don't actually have an empty operation. Sorry. Okay, if low of X is empty. I think actually, is that this operation, this one you're talking about? Yeah, okay, good. So we'll get there, right. We want to do that. But this is just a call to insert, right? This is a recursive call to insert. I want to insert now low of X into the widget with label high of X. Okay, the notation for that was sub W high of X. That's all it is. This is just using recursion. Now I want to set the non-empty bit. This was a summary bit. Okay, non-empty corresponds to summary. Okay, so now I'm storing the summary bits in a new widget called the summary widget. And so how should I write this line recursively? Yeah.
Insert high of x into the summary widget.
Insert high of x into the summary widget, right? This is like pattern matching, right? We did low and high here. Now we're doing high in the summary widget. So insert high of x into summary of w. Okay, so the point is, when I insert an element x, first of all, it belongs in some subwidget. And so I'll insert it in that subwidget. And within the context of the subwidget, the index inside the subwidget is low of x. Okay, and the number of the subwidget is high of x. Second, if that subwidget was empty, I have to now mark that it was non-empty. So I do that by marking in the summary widget that the widget whose name is high of x is now non-empty. So that's done by an insertion. So these are two recursive calls. Okay, so what is the recurrence for the running time, t of u? What's the running time of this algorithm, just as a recurrence? That's the easy part. So you should imagine these lines are now crossed out. I've replaced them with these lines. Just two lines. Okay, you have to think of the sizes. It's the standard recurrence, right? So there's
2t square root of
2t square root of u, right? Plus order 1, exactly. Okay, there are two subproblems. Each subproblem is a psi squared of u, right? The subwidget is a psi squared of u. The summary widget is a psi squared of u. That's what it says up there. Okay? So I solve those two subproblems, and then there's this combining cost. Well, that's just the calls, so that's constant time. Okay, so what's the solution to this recurrence? Maybe it's easier if I do the substitution we did before. Okay, if I look at t of log u, then I'm dividing log u in half. And now I can apply the master theorem, right? So what's the solution to this recurrence? Yeah.
just
Log u. Oh, that sucks. We wanted log u. So why didn't I get log u? This is sort of a tautology of, no, just pointing. Got log u. I wanted log u. When did I get log u? What was different in the recurrence? The coefficient was 1, right? This was a 1. This is the number of recursive calls I make. So here I made 2 recursive calls. I got log u. I wanted to make only 1 recursive call. So now comes the hard part. I have to do only 1 recursive call and finish this off. Okay, so this is not quite there yet, but that'll be the next step. Okay, let's first do successors. Okay, I'm getting low on time, so I'm going to have to start filling in some details. Okay, so here's, again, we'll do recursive calls with successor. And we sort of pointed out how we're going to do it. Each of these 3 operations was a successor operation. Okay, I'm basically copying this code, but filling in the recursive calls instead of writing it in English. I'm also adding in some new notation, which is sort of the inverse of high and low. So what we're doing here is it says, I want to find the successor recursively in the subwidget that contains my x. Okay, so I start at low of x. That's exactly what this first line is saying. Start at low of x plus 1. Okay, the successor of low of x will start there. And I want to look in the subwidget called high of x. If I found something, then I return something less than infinity. And then, well, that's my answer. Whatever the successor thing found was the successor of x. The trouble is that successor is within the subwidget. I have to bring it out to the whole widget. Okay? The subwidget only has square root of w things, but I need to talk about w things, size of w. So to scale that up, this is the offset within that widget, but I also have to say, well, the index of the widget was high of x. Multiply that by square root of w. Those are the high bits. The low bits are whatever I found. Okay, so that's what that's doing. It's the inverse of high and low, reconstructing a full number. And otherwise, if I didn't find something, I do these two steps, and that corresponds to these two lines. So first of all, I find the next non-empty subwidget. To do that, I look in the summary widget. It tells me which widgets are non-empty. I start at high, or just after high. So start at I greater than high of x. I find the next one that's not empty. That's I, just like before. And now I look at that ith subwidget, look at the successor of minus infinity. That's the smallest element. And I'm done. Okay, trouble is, this makes 3 recursive calls. Okay, this is even worse. And the running time will be not just logarithmic. This actually works out to polylog n. So it's log n to the log base 2 of 3. Okay, with a little bit more than 1. About 1.4. Okay, so that's the running time of this algorithm. So we're not there yet, but we're almost there. Okay, and I want you to think about how we can make these algorithms better. Let's think about successor first, because that's the worst algorithm. So it's the highest nail to knock down. Okay, let's analyze successor. There are 2 cases to successor, right? We might find it in the first step. Then we only make 1 recursive call, so that's good. So if successor of x is in the widget that contains x, then we're in luck. There's only 1 recursive call, and that we can afford. So then, OK, there's 1 recursive call. Otherwise, then there's 3 recursive calls. Okay, there's 2 more. There are 3 recursive calls. The first one, what does the first recursive call do? Well, it just found infinity, so it didn't tell us very much. It just told us that we're in the else case. Okay, so the first one, we just learn that successor of x is not in the widget containing x. The second recursive call, the I line, is saying, well, find the next non-empty subwidget. Okay, that's pretty fundamental. And the third call is saying find the minimum. Find the smallest element in the subwidget. Okay, I claim there are two improvements I can make here. Two ways to do these steps faster. So who sees either one of them? You should think back to augmentation. What could we maintain that would make some of these steps go faster? 2 out of 3. Yeah. Store the minimum and maximum. That's both. Great. Those are the two improvements. That's all you have to do. Store the minimum and maximum of each widget. Okay, then this is really easy. Finding the minimum, well, I just compute min of the widget I'm looking at. Okay, here, what widget was I looking at? Widget I. So sub wi. Okay, and there it is. Now I can do that in constant time instead of a recursive call if I maintain the min. Why did you want to maintain the max? In other words, how do I do this step? Yeah, you have an idea?
If the element that you're is the max, then you just forget about it.
Right.
It won't be in there. But if it's not the max, then it's obviously in there.
Right. If the guy you're looking for, you look at x. Is x the maximum element in your list? Well, if it's the maximum element, you know that the successor is not in there because you're the max. Also, if you're bigger than the max, you know that the successor is not in there. Okay, remember, the elements we're looking for may not be in the set already. So it may be bigger than the max. But also then it's definitely not in that subwidget. We have to look at the next non-empty subwidget. Okay, so this is equivalent to testing that x is greater than or equal to the max of the subwidget that we care about, which is high of x. Okay, so that's the comparison that's relevant. I don't have time to rewrite the pseudocode, but that's what's going on. We want to learn, so we can check if we want to know whether we're in this case or we're in this case, which is what step 1 is doing, then we just make this test. If x is less than the max, as you said, we know that the successor is in there, so it's just one recursive call. If it's more than the max or greater than or equal to the max, then we're going to have to look at different subwidgets. And we know this in constant time. This only takes constant time to check. Okay, a lot of things going on here. This is only the 4th step, and there's one more step we need. Okay, this will make successors go fast. Right? There used to be 3 recursive calls. Once we do all these changes, there's only 1 recursive call. Okay, and it takes order log u time. So this gives us the desired behavior. Either you're in this case, in which case you just look at the subwidget that contains x. Or you're in this case, in which case I just look at the summary widget. I just find the next non-empty subwidget. And that's essentially all I have to do, because once I find that widget, I just take its min in constant time. So the heart of what's going on in the second case, in the else case, is that I have to look in the summary widget recursively. And I only have to go one way. And that's why it's log u. Okay, so that's good. Insertions are our next problem. Okay, this is standard augmentation, right? So we know how to maintain the min and the max of each widget. Whenever I insert, I just check whether the guy I inserted is smaller than the min or larger than the max. If so, I update them. Okay, that's easy. The trouble is, with insertions, there are 2 recursive calls, and I can only afford to do 1. So I need to fix that. This is maybe one of the... We're almost there. Successors are fast. Insertions still take logarithmic time. So any ideas how to make this better? So maybe I should do the same kind of analysis. Okay, this is the fifth step. Okay, there are two cases in insertions, although I haven't written it that way. Consider this insertion, the second insertion. I insert into the summary widget. Well, it might already be there, right? Then I don't have to insert. Okay, so if we know that the subwidget sub w high of x is non-empty already, and we're inserting into it, we know it's already recorded in the subwidget. So then we only have to do one recursive call. We just insert in the subwidget, and we don't have to worry about the summary widget. So that's good. That'll run fast. Trouble is if it was empty. So this is a special case, right? If I'm inserting into an empty subwidget, that means after the insertion, it'll only have size 1. So I could afford to do something special here, not insert in it right away. This subwidget has size 1. What could I do? Where could I put? I want to insert x into an empty subwidget. Where could I put it? Okay, I don't want to have to do a recursive insertion. That'll cost too much. So I've already, in this else case, I also have to recursively insert into the summary widget. Okay, so that costs a lot. That costs basically all the time I have, because I can only make one recursive call. How could I do this fast? Insert into the subwidget. It's empty. Well, what else do I have? I mean, a widget that has subwidgets, has summary widgets, yeah.
Put it in your min-max field?
Put it in your min-max field, exactly. Okay. So just put it in your min and max. And I'll concentrate on min. So the idea is that min of w is not recursively inserted, ever. Okay, this is a change. I'm changing my data structure so that instead of min just being some record of what the min is in this widget, it's a real number that's not stored anywhere else. Okay. Min is not recursively inserted. It gains prominence, it gains importance. Right? I have to care about the min. It's not hard to care about the min because there's only one of them. But this makes insertion go fast. All I have to do is set the min. If there's no recursive insertion in this, I mean, it seems like an easy case, right? My widget is empty, so I can just put something into the min. Okay, the min won't be occupied yet, so I can just put it there. When it's non-empty, well, then I'll recursively insert, and I don't have to worry about the summary widget. So in either case, we're sort of trivially OK. And it will only take order log n time, log u. OK. Why don't I just write the pseudocode for the new insertion algorithm? Okay, this is the last idea. So we had 5 ideas along the way. That was a lot. Okay, there are a lot of ideas that go into this data structure. But each one is pretty simple. Okay, and you'll go back over your notes, hopefully. And you can read the notes that are online, which go into some more detail than what I wrote here. And each idea is not too hard. Think about it for a while, you'll see, oh yeah, I could have come up with that. The hard part is that you needed 5 ideas to get all the way. Okay, so there was a lot to this data structure, but the result is so beautiful, I think, that it's worth the effort. Okay, this is hard stuff. But getting log time is just so cool that I wanted to share it with you. Okay, this material, as far as I know, has never been taught in this course before. It's usually only graduate material. But you guys are smart. So in the end, okay, I think everyone here came up with the ideas. I didn't do very much. All I did was follow along with what you were doing. Okay. All of these ideas are in you. This is not hard to come up with. Because you're smart. Okay, that helps. Right, flattery is always fun. Don't let it go to your head. This is still not easy stuff, but this is like research quality stuff. Okay, this was a big result when it came out, as you can imagine. So this is just saying what we said. I'll repeat it, so this will drive home the last idea, the fifth idea. Well, we have to deal with the min if we're doing an insertion. So you say, well, if we're inserting something smaller than the min, well, that's our new min. So we'll swap what we're trying to insert with our old min. And now we'll try to insert the old min, because it's no longer the min, it's bigger. Okay, that's just a technicality. This is the heart. This is very short code. Okay, there's one more line, which is you have to update the max. Okay, but that's easy. The heart just says, well, check whether this subwidget is non-empty. So I didn't mention it. Each subwidget can store whether it's non-empty. You could just look at the min field and see whether that's nil. Okay, this is easy. And if it's non-empty, I'll just recursively insert there. If it's empty, I'll just recursively insert in the summary widget. And I can store it in the subwidget just by setting the min field. That's it. So there's only one recursive call in either case. And so this runs in order log u time. And that's it. These algorithms are also written on your problem set because there's a question about them. So